Okay, now we're going to come to a concept of natural numbers. Now, what I want you to understand is the natural number is a specific number. It's the number e. Now, I know you're looking at that and saying that's a letter, that's not a number, but just like pi is approximately 3.14, e is approximately 2.72. Now, the actual mathematics behind it is that it is equal to 1 plus the reciprocal of n raised to the n power. And it's all of the terms added together as x approaches, it's the limit as x approaches, or n approaches infinity. It's a calculus term that you're going to get into next year. But for right now, I just need you to understand that the number e is approximately 2.72. And if we wanted to graph this function right here, y equals e to the x, well, what's my initial value? My initial value is right here. It's 1. Because we don't have a different number. The base, the growth factor, is e. And so the growth factor is 2.72. So this graph passes through 0, 1. It passes through 1, 2.72. And this number right here is 1 over 2.72. In other words, it's the reciprocal of e. This is e squared. But it's still a growth function. If you look at it, it still approaches y equals 0 as x is negative. It approaches infinity as y is positive. It's always increasing. This is 1 comma e. This is 1 comma e squared. This would be 1 comma e to the 0, and e to the 0 is 1. This would be negative 1 e to the negative 1, or 1 over e. So it's still a growth factor function. So in other words, when I have the value of e, when I look at it as the natural number, what if I wanted to transform that function? What if I wanted to take that function and do something to it? Well, if you look, there's two things that have happened. One is that up here in the exponent, we have a transformation. And when it is happening in the exponent, we know that that is a horizontal transformation. And this transformation is telling me to move right 3. So if I took all of these values and I moved them to the right 3, to where my new point would be at 5, 7.39, and 1 plus 3 is 4, 2.72, and 0 plus 3 is 3, 1, and doing the same with 1, 2, 3 here, and 1, 2, 3 here, that I have a function that has moved to the right 3. But there's something else that's happening to it. What else is happening to it in this problem is that all of my y values have to now become negative, because this is a vertical or reflection over the x-axis, meaning I'm going to change all of my y values to negative. I'm going to reflect each of these values to its negative value. This point right here, instead of 3, 1, will be 3, negative 1. And instead of 4, 2.72, it'll be 4, negative 2.72. And instead of 5, 7.39, it will be 5, negative 7.39. And this graph reflects over the x-axis. This right here is the graph of negative e to the x minus 3. That's e to the x moved right 3 and reflected over the x-axis. Well, what has that done to the domain? Nothing. All real numbers is still all real numbers. But what did it do to the range? The range is now under the x-axis. My range is no longer y is greater than 0. My range is y is less than 0. My horizontal asymptote, however, is still y equals 0, because this is going to approach, as x is negative, closer and closer to 0. Okay, so that's transformation of functions. What about solving them? What about solving a problem that looks like this? What about solving 2 to the 3x minus 1 equals 32? Well, that might be very hard to do, except we have one more property that we're going to deal with today. And it says if the bases are the same, if I can get both sides to have one single base that is the same, then the exponents would be equal to each other. That's a u and that's a v. And so if I can get the bases the same, we can ignore them and just say u equals v. Well, you're going to be getting, we talked about this in class, you're going to be getting this table or something very similar to it when you are working on your non-calculator tests and quizzes. And if you'll notice these numbers right here, I've got a base of 2 and then the number 32. Well, a base of 2 is the lowest I'm going to go. So 2 to the 3x minus 1 is just going to stay the same. But where on this list can I find 32? 32 is right here. 32 is, that's 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So 32 can be rewritten as 2 to the fifth power. Why did I want to do that? Because now when the bases are the same, I can ignore them. And I can look at 3x minus 1 must be equal to 5. Add 1 to both sides, so 3x equals 6. Divide both sides by 3. X equals 2. Now let's check our work just to make sure, because every once in a while we'll find an answer that it looks like it works, but it really doesn't. Let's plug in 2 into this problem. That's going to be 2 raised to the 3 times 2 minus 1. That's 6 minus 1, that's 2 to the fifth, and we know 2 to the fifth is equal to 32. We know that this is a true statement, so we have solved the problem. This statement is true whenever x equals 2. Now b looks a little scarier, and it only looks scarier because it has e's in it, but the concept is still the same. The first thing I have to recognize is I need a common base. This one is a base of e, this is a base of 1 over e, and this is a base of e again. I need them all to be the same, so I'm going to choose base of e. This one is fine, we're going to leave it alone. Instead of 1 over e to the 3x, remember, I don't want that fraction, I just want e, so I'm going to make that negative 3x. This is a power raised to a power. We had a property, told us what to do with that. When it's a power raised to a power, we multiply these two numbers together, and that's going to be e to the negative 4x. We had a law that said if we're multiplying with the same base, we can add our exponents. So negative 3x plus negative 4x is negative 7x. And now we have one base that's the same on both sides. We can come through our problem, mark out the e, and now simply solve 2x minus 1 equals negative 7x. Subtract 2x from both sides, negative 1 equals negative 9x. Divide by negative 9, 1/9 equals x. And I'll leave that up to you if you'd like to plug in and prove that that actually works. This is our unit on exponential functions. Here's a summary of when the function is a growth function. This is the summary of when it's a decay function. And this is the summary for how to solve, ensuring that the bases are the same, so we can solve using exponents without a calculator. Good luck.